Settle in, everyone. We're about to dig into some really interesting source material you've shared with us. Today, we're unpacking an advanced EMG signal simulator.
Right, EMG. And just quickly, that's electromyography. It's basically, a technique for measuring the electrical buzz muscles give off when they work.
Listening to muscles talk, essentially.
Pretty much, yeah. And this source describes a web app, a simulator, built to let you record and visualize that EMG data. Looks like they really aimed for a user-friendly interface.
Yeah, making complex stuff approachable. So our mission, let's say, for this deep dive, figure out the core features, and maybe more importantly, what this simulator actually helps us explore about these muscle signals. Like, what do you learn by playing with it?
Good question. So the source lays out the basics first. Generating a signal, you've got standard controls, start recording, stop recording, simple enough,
Makes sense. Start, stop.
and a clear data button too, to wipe the slate clean.
Okay. But the interactive part seems to be this flex button.
Exactly. That's kind of the core simulation element. You click it, you hold it down, and that simulates a muscle flexing. The source even mentions it turns yellow, so you get that visual feedback.
Ah, okay. And when you let go.
Simulation stops. The muscle relaxes, electrically speaking.
Right. And that action, that clicking and holding, it translates into this electrical signal you see on the screen.
Precisely. And here's where it gets interesting. You can control the character of that signal. There are sliders for that. First one is the noise level slider.
Noise. Why simulate noise?
Well, real biological signals are never perfectly clean, right? There's always background electrical activity, maybe some interference. This slider lets you add that in. You can see what a slightly messy or a very messy signal looks like, which is, realistic.
Okay, so it adds realism. Makes sense. What's the other slider?
The flex level slider. This one controls the simulated intensity of the muscle contraction.
Ah, so like flexing harder versus just a little twitch?
Exactly that. Crank up the flex level, you simulate a stronger effort. And you see that reflected in the signal, usually a higher amplitude, taller peaks.
So you can directly see how effort impacts the electrical output. That's cool.
It's fundamental for understanding EMG, yeah. How signal size relates to, well, force or effort.
All right, so we're generating signals, we're tweaking their intensity and noise. How do we actually view this data effectively? The display options.
Yep. There's a time window slider. This adjusts how much time or how many data points you see on the graph at once.
Like zooming in on a short burst or zooming out to see a longer period?
Exactly. Lets you focus on details or see the bigger picture.
Useful. And a grid. I see a show grid checkbox mentioned.
Yeah. Just adds horizontal and vertical lines to the graph. Makes it easier to, estimate the actual voltage values by eye. Standard graph feature, but helpful.
And Autoscale. What's
Yeah.
that do?
If you check that box, the graph automatically adjusts its vertical scale, the y-axis, to fit whatever signal is currently displayed. So if you have a really small signal, it zooms in. If you suddenly have a huge spike from a strong flex, it zooms out so you can still see the peak. Keeps everything visible.
Okay, keeps things tidy. Now, it's not just about the visual line, is it? The source says it provides real-time metrics, numbers,
Correct. 3 key ones are highlighted. First is peak amplitude.
which is just the highest point the signal reaches.
Yep. The maximum value recorded in that little window of time gives you an idea of the sort of maximum instantaneous electrical activity.
Okay. Then there's RMS value, root mean square. That sounds a bit technical.
It does, but it's super important in EMG. Think of it not as the peak, but as the overall effective level or power of the signal over time, like the average signal strength, but calculated in a way that properly accounts for the ups and downs. It gives a much better sense of the sustained activity level than just a simple average.
So peak is the absolute top spike. RMS is more like the general energy level.
That's a good way to put it, yeah. RMS is very commonly used to quantify muscle activation,
Gotcha. And the last one mentioned is mean value.
which is just the simple mathematical average of all the data points in the window. For typical EMG signals that fluctuate around zero, the mean might not be as informative as RMS, but it's still a basic statistical measure the simulator provides.
Right. And the source ties these metrics back to real-world uses.
It does. It mentions things like muscle activity analysis, maybe tracking fatigue, or even uses in rehabilitation monitoring how muscle activation changes over time as someone recovers. Understanding peak RMS mean is key there.
And it really pushes you to experiment, doesn't it? Change the noise, change the flex level, see what happens.
Absolutely. That seems to be the core idea. Learn by doing. See how cranking up the noise might make it harder to get a stable RMS reading, or how the peak amplitude jumps way up with the flex level.
Okay, so let's wrap this deep dive. We've seen this EMG simulator provides this really hands-on way to explore muscle electricity. You can generate signals simulating flexing, tweak them with noise and intensity, view them clearly with display tools, and get key numbers like peak amplitude, RMS, and mean value in real time.
And the big takeaway from the source seems to be
Yeah,
play with it, experiment. That's how you connect the controls to the output.
right. Which leads us to a final thought for you, the listener. The source material really encourages you to experiment, change the noise, change the flex intensity, and watch how those metrics like peak amplitude, RMS, and mean value react. So think about this. What does observing those specific relationships in the simulator, how noise affects RMS, how flex level affects peak pick? What does that teach you about the real world challenges and, let's say, the nuances you face when trying to interpret those same metrics from messy, complex EMG signals coming from actual human muscles? Something to ponder.